You are now well on your way to becoming an expert coder and elite computer hacker. This past week in Foundations of Algorithms, we learnt about control structures, if, else if, and else, along with switch statements. We covered order of operations and a whole bunch of different operators, along with all their traps and tricks. We also covered loops, for loops, and while loops, with a brief mention of do-while loops. We're setting ourselves up for an exciting next week. Pointers and arrays are on the table, and pretty soon, control of the entire world will be at your fingertips. I hope you're looking forward to the next week of Foundations of Algorithms.
And we are back to another exciting week of Foundations of Algorithms. So as promised, at the start of every week, we do have our historical figure. Did anyone see the movie Hidden Figures? Space movie? Okay, do you know who this is? Yeah, so Ella saw the movie Hidden Figures, which is about a group of women programmers at NASA who were responsible for the vital trajectory calculations that led to many of the successful US space missions. So Katherine Johnson was born in 1918 and only passed away 2 years ago. She spent 30 years working at NASA and in an office of what they called colored computers. By computers, they meant individuals who actually performed complex calculations, because the term computer only came to mean machine after in the modern era. Prior to that, a computer was an individual who was adept at calculation and would perform the same types of calculations that we now do rely on machines to perform. However, Katherine Johnson, other than being an important pioneer in space trajectory calculations, also worked on digital computers. So she was not confining herself to the pen and paper ones. She, in fact, calculated the trajectory for Apollo 11 on one of NASA's early computers. So that's our little history piece for the week. Highly recommend watching this movie. I think it even may have won an Oscar or two, and which is on topic for this week. So where we left off last week was talking about recursion, and let's do a bit of a warm-up exercise to get us back in the groove. So here we have a representation of the triangular numbers starting with 1 and going up to 21. And the thing that's interesting about the triangular numbers is if you have a bunch of objects and you take the triangular number, if you have the same number of objects as the nth triangular number, you can always arrange those objects in a perfect triangle structured like this, where the bottom row has, say, k items, the second last row has k minus 1, the third last row has k minus 2, etc., etc. So this naturally gives us the question, how do we calculate the, say, the jth triangular number? So one way to approach this would be to try all the numbers and then see if you can arrange things in this order. But as we saw before, brute force approaches can be pretty inefficient. So what can we do? We can break up the problem like this. So if we know the first triangular number, we look at the number of items in the first triangular number, 1, and then we take 1 and we add 2 to it. So we have the solution for the first one, and then we add something to the solution for the first one. So now what about the third triangular number? To get the third triangular number, we can take the second triangular number and add 1 more than the number of items in the last row of that triangular number. Or another way of saying 1 more than the number of items in the last row is just say j, where j is the jth triangular number that we're looking for. So if we're looking for the 6th triangular number, we add 6 to the 5th triangular number, and that gives us a pattern that's pretty easy to code up. It looks something like this. We have our function int trec that's just going to calculate our nth triangular number. If n equals 0, return 0. There are no numbers in the 0th triangular number. It's just the number 0. That's our base case. Otherwise, return n, which is the nth triangular number that we're looking for, plus the sum total of objects in the previous that we would have needed for the previous triangular number. So this is the same thing as saying if we are looking for the 6th triangular number, add 6 to the solution for the fifth triangular number. What's the solution to the fifth triangular number? The solution to the fifth triangular number is 5 plus the solution to the fourth triangular number. And that's essentially what we've got in our else statement over there, is we say return n plus the solution for the n minus 1th triangular number. So let's see what this looks like in our code. We have two different ways of calculating the triangular number in this program. We have our iterative and our recursive solution. And there is a deep fact that for any problem you can solve iteratively, you can solve it recursively, and for any problem you can solve recursively, you can solve it iteratively. What's the secret to figuring out how to convert from one to the other? The secret is a data structure called a stack, and that's going to be one of the interesting things we'll learn about this week, is our first real data structure other than from our intro lecture. But more on that later. So here's our iterative version. If you want to calculate the nth triangular number, we have the sum, which is how many up to so far. And then for every row, add the number of items that should be in that row. So that's one version of the solution. Works perfectly fine. In fact, it's probably even going to be the faster and better solution to this particular problem. But this is our toy example. So let's try the recursive function anyway. So here's our recursive one, as we saw before. If n equals 0, we have our base case. The case that happens when we get to the bottom of our calculation, because you can't ask what's the negative first triangular number. It doesn't make sense. We have to have some place where it stops. That's our base case, and if you're writing a recursive function, always make sure that you have a base case, because otherwise it'll just keep recursing and recursing and recursing and recursing. And then we have our recursive call. So you see here, we've actually used the name of the function itself within the function, and this is what makes it recursive, looping it in on itself. So let's give this a run. This should probably surprise none of you. Enter n. We see both of the solutions come up with the same outcome. Great, so that seemed to work. Let's take a look at what's actually happening inside the computer's memory. We'll look at this a few different ways, but this is the most simplest and schematic way that we'll look at it. This is for our recursive version of the triangular numbers. During the first call to TREC, the first time we run TREC, let's say we ask for the third triangular number. You can see in the corner there. There I've asked for the third triangular number, and to calculate the third triangular number, it's 3 plus the second triangular number. When the program hits that point where it sees TREC2, the computer creates a whole nother copy of TREC inside the computer's memory and puts it on top of the other one. This is TREC2 over here. And for TREC2, the way this works is it gets a return statement, and that's 2 plus TREC1. So what does the computer do? Puts another copy on top. TREC1, it's 1 plus TREC0. TREC0, what do we do? Someone who isn't Joseph? Oscar.
Return 0.
Well, we've got to first call TREC0, so what do we do?
Add another one on top.
So add another one on top, and remember this is our base case, so we return 0. And now if we return 0, we now have the solution to TREC0, so we can do 1 plus TREC0, which is 1. And now we have the solution to TREC1, so this goes back to TREC2. That's 1 plus 2, that gives us 3. And now we have the solution to TREC2, so it's 3 plus 3, that gives us 6. We're done. Okay, so works pretty easily. We can understand that one for the triangular numbers. Now let's move to our teaser problem that we had at the end of last lecture. This was the Tower of Brahma, also known as the Towers of Hanoi, which if you get a chance, I would go online, we'll post the link, play a version of the game yourself to get familiar with how to solve it. So if you remember, we had these disks, and the goal of the game was to move all the disks from one pole to the other. And the legend had it that, remember, there were these monks who had to move them from one disk to the other. They had 64 of them, and if they managed to move them all, the universe would end. So one of our motivating questions for today will be, will the universe end if we're playing this game and moving the disks at a reasonable pace? But let's first get to our technique for solving that we discovered last lecture. Our technique for solving was a recursive solution And the way it worked was first to solve the puzzle for one disk. And how do we solve the puzzle for one disk? You did? Yeah, we just move one disk to the other pole. We move the disk from A to B. So we know how to solve it for n equals 1. And then for n equals 2, we moved the top ring onto a pole, the same as we did in step 1. So let's move it onto the third pole. Then we move the bottom ring onto the final pole, the one in the middle. And then we move the smallest ring back on top. So you can probably get that in your head. And then to solve the puzzle for n equals 3, we used what we had in step equals 2, which is how to move 2 rings onto any pole. So we move the top 2 rings onto the last pole, we move the bottom ring onto the middle pole, and then move the 2 top rings again to the middle pole, because we know how to move rings as a general state, as a general statement, kind of by induction here. So we know, if we know how to move it for 2, then we know how to move it for 3, because moving 3 is the same as moving 2 plus this extra step in the middle. So this allows us to solve the puzzle for n equals k by doing the solution k minus 1. We move the bottom ring onto the final pole, and then we solve the puzzle for k minus 1 again, moving that entire stack into the right place. And if that was too wordy for you, I encourage you to go back to the prior lecture recording and see the worked demo of it there. So the intuition to our problem is that solving the problem for k minus 1 leaves 2 rings that we can use. So we have our 3 rings in total, 1 ring which is our auxiliary ring that we're going to use as a temporary holding space for the pile of k minus 1 disks, and then we only have 1 ring left that we can move between the other 2 poles pretty easily. So if we add a single larger disk, as it says here, onto one of the 2 spare rings, we still have 1 left, and we can just move the pile, the k minus 1 pile again, in order to win. Let's look at the code for this. I will scroll up and check out hanoi.c. And we're going to see 2 versions of it, a more advanced version, which you don't have to understand the code for now, but it'll just give it a more illustrated depiction of what's actually happening. So we have our function signature, and there's something new here. There's the key, the return type void. When you think of a void, what comes to your head? Nothing. So what is it going to return? Nothing. Stands to make sense. Then we have 3 arguments, 3 characters, from, via, and to. So this gives us a sense that we want to move our poles from a given pole to another pole, and we'll have our third pole, our auxiliary pole, which we'll call the via pole. And then, of course, we need to know how many rings there are so that we can solve the puzzle for n minus 1. Now, this is the first time that you'll see us actually using argc. Argc is the count of how many arguments I've actually given the program itself. So if I were to type in the command echo hello there FOA, hope you are great. Argc will be 1, 2, 3, 4, 5, 6, 7, because there are 7 arguments on the command line, each separated by a space. There you go. Echo runs. Echo is another one of these built-in programs. It does pretty much what you'd expect from its name. It gives you right back what you put in. Then we have this funny function, a toy. Don't worry about it for the moment. And argv. Argv is the way that we actually store the program arguments and can access them back. So essentially what this line is doing is it's taking the value n, it's asking us how many rings do we want, but instead of using scanf to get you to type it in once the program is running, it allows you to start the program off the bat with an argument that tells the program how many rings you want. We'll get back to this syntax a little later. So then we say if there are less than 1 argument, which means the user hasn't said how many rings there are, print an error and fail. Once that's done, we now have everything we need to run our program. We want to move the rings from A to B via pole C, using pole C as the storage space for all the remaining rings, and we want to do this for n rings. Okay. Now this code is a little bit tricky. We're going to step through it somewhat now, but I encourage you to go and play around with it on your own. And I think we'll also post the version that displays more what's going on, even though with that version you're not expected to know understand all the way it works yet. So here we go. First thing, what is this called? We talked about it already with Trec for our triangular numbers. That's our base case. And we called this what do we call that? Called that the recursive call, because it's the same function as up there. All we're doing here is printing some things, so don't worry about that. This is just helping you to show what's going on, a print there and a print there. And then we have another, what do I call this? Recursive call, yeah. So what we first do is we solve the puzzle for n-1 disks. And the way we do that is by using the via pole as our final destination. So we've said solve the puzzle from move n-1 disks, move it from pole A to start with to pole C via pole B, using pole B as the extra pole. And the reason we've switched this round, the reason we aren't saying move n-1 disks from pole A to pole B is, remember, when we start the problem, all the disks are on pole A, and our goal is actually to move n-1 disks to pole C, because we move the disks to pole C, and we move the bottom disk to pole B, and then we move all the disks from pole C back onto pole B. So this, in the case of the very first call that we make, obviously it's going to change as we get further and further into the recursion, we have swapped via and to because we want to use the auxiliary pole as our destination. Okay? Once we've done that, we move the largest disk onto the place where it's meant to go. We're moving it onto the 2 pole. So moving a disk from the original place to 2. So this is like moving the largest disk from A to B. And then we have to move the n-1 disks again. We move them from which pole? From C back to B. Now, remember that once we've started moving the disks around, which our auxiliary pole is going to change, because if we want to move 3 disks from A to C, then we have to first move 2 disks. And to move 2 disks, that we're going to use a different auxiliary pole each time. And what the switching of the to, from, and via is doing here is it's just switching up which pole we're using as the auxiliary pole each time. Now, I'm not going to step through how that works for all the different recursive calls, because we would be here for ages, but let's give it a run. And what I'm actually going to do, even though I've got this beautiful file, hanoi.c, Liam over there has prepared for us one which actually has a clearer output, which is more complicated. This is the complicated display one, but the code underlying it, the actual substance of what's going on, is exactly the same as the normal Hanoi. So let's run v-hanoi. Let's run it with 3 disks. And it has this very nice output that we can see. So we start with all the disks on A. Okay, move a disk, one from A to C. So we've moved that top disk. Move a disk from A to B. Move a disk from C to B. And now we have 2 disks on B. Oh, in this case, there is a subtlety here. Who can see what mistake I've kind of made / what the program has made? Let's take a look. Where have all our disks ended up? C. And what was I just talking about? What did I say was our goal when I was talking before? Yeah, I said we wanted to move them to B. This instance of the program moves them all to C. So it's using B as the auxiliary pole. It doesn't really matter which pole you pick as the final destination and which pole you pick as the auxiliary one at the start. That's just how you set up the problem. So if you have the child's game in front of you, the goal is to move all 3 of the disks onto a different pole in order. It doesn't really matter which you call the solution. So in this case, we've just said the solution is moving them all to C. So let's go back a little. We first move 2 disks onto B, and these are the steps with which we solve n-1. To solve n-1, we first had to solve it for n equals 1, and we solved n equals 1 by moving a disk onto C, moving the larger disk onto B, and then moving the smallest disk on top of that. So now we've moved them all onto B, and by now you're probably getting tired of me saying A, B, and C, so we'll leave it there. You can look through the output yourselves. So this takes us back to our motivating question of, so great, you've got this kids game. What I really want to know is, will the monks be able to end the universe? Because, I really want to graduate with my degree. I've got this whole great career plan. I want to have a family. Can I do this before the monks finish? Let's see. So this is what we call a recurrence relation. It's a way of figuring out how long a recursive program is going to take, parameterized by the input. So let's say we have n disks. This is a relationship that tells us how long the program runs. Now, Doris, there's something tricky about this. Why might I struggle to get the answer here? Okay, so I've asked you for the answer of t of n, and the answer to t of n, what is that answer? What do I need to know first? T of n minus 1. So I've defined this thing in terms of itself. So how do I get the actual answer if every time I ask you how many cakes are there, you say, well, there's one more than 1 minus the number of cakes there are. That doesn't tell you how many cakes there are. So this gives us a bit of a problem. But you can see how we've at least constructed this representation. So I've said the amount of time that it should take is the amount of time that it takes to move the smallest stack, which is n minus 1, plus 1 to move the biggest disk, and then moving the smallest stack again. So that's two of the smallest stacks, and then 1 of the biggest stack. But I have one extra piece of information. I know how many steps it takes to move how many disks? One disk. How many steps does it take to move one disk? One step. Okay, so maybe I can use that. If I know that I need to solve this for 3, then I can write the same expression for solving it for 2, and solving it for 2 will have an expression that asks me solving it for 1. And so what I could do is just substitute it back in. I do solve it for 1, and then if, let's say, n is 2, that gives me 2 n minus 1, and n is 2, so that's 2 of t of 1 plus 1. And what's t of 1? How long does it take to move one disk? 1. So what's 2 times t of 1? 2, and 2 plus 1 is 3. Great, you've just passed grade 4. So we can work it out for 2, and then so presumably we can work it out for 3. We call these recurrence relations. So let's try and come up with a more systematic way of solving it that doesn't require me taking all of you back to primary school. So we have our relationship 2 of t of n minus 1. Let's just write it out what it is for, and write out the solution for t of n minus 1. So this is equal, following the rule above, t of n minus 1 is equal to 2 times t of n minus 1, and then plus 1 to move the largest disk again. And then I can do this again. I can do t of n minus 2 equals 2 of t of n minus 3 plus 1. You're getting the idea. Now we can do our fancy substitution thing, but let's do it algebraically instead of concretely with the number 1. So I have our 3 equations, and now I can do some substitution. I substitute 3 into 2. I substitute 2 into 1. And now I have 2 to the power of 3, t of n minus 3, plus 2 squared, plus 2, plus 1. Does anyone see a pattern? Monica, can you see a pattern happening here? Yeah, so there's a pattern here. Monica, your voice is a little quiet. Why don't you say that a bit louder? So let's get it in the microphone.
Okay, so we have 2 to the power 3 and 2 to the power 2 and 2. So we can find if n minus 3, then we times the 2 to the power 3.
Yeah, so we have our biggest power of 2 at the front. And then this is going to get larger and larger and larger depending on how large n is going to be. So if we had a 4th substitution in, what would our first term be?
2 to the power 4, t n minus 4, and plus 2 to the power 3, and plus 2 to the power...
Yeah, you've got it, you've got it. So we've got a pattern here that Monica illustrated for us. So what about instead of just substituting n minus 1 and n minus 2, we keep going. So we get, let's say the number of times that we do this is k. We have k substitution. So we get 2 to the power of k, t of n minus k, plus 2 to the k minus 1, plus 2 to the k minus 2, et cetera, all the way until we get back to 1. Now, how many equations do we have to substitute? Let's say we had n disks. How many times can I repeat this process? Oscar, yeah, we can repeat it n minus 1 times. So let's set k to be n minus 1, because eventually we don't need to keep solving it and keep solving it. Eventually we get back to 1, which is the base case. How many times can we do this? N minus 1 times. So now we substitute k equals n minus 1 in here. We get 2 to the n minus 1, t of 1. And what's t of 1? 1 plus 2 to the power of n minus 2 plus 2 to the power of n minus 3. And now we can actually just figure this out, because we know what n is. N is the number of disks. and this gives us a closed form solution. Has anyone seen this kind of pattern before? Know what it's called? So that was our base case. We have this pattern, which is just the geometric sequence. Now, for those of you who haven't seen the geometric sequence in class yet, it's nice because it has a closed form solution. If we know that this is the pattern of the sequence, we can just compute our answer, which gives us 2 to the n. And there's a -1 in there, but do we really care about one step that the computer does? No, why don't I care about the one step? Someone new for today.
You don't really care about the one because you're trying to see like how it scales.
Yeah. Michael's right. The point of this maths is to figure out how long the program runs, and if the program takes one extra computation, how long does like one computation take on a computer? Like if I want to do like one addition, it takes pretty much no time at all. So I really don't care about +1, -1, +5, -5. The whole point here is this 2 to the n, because that tells us if I add more rings, I'm going to get exponential behavior. So solving it for 4 rings is going to be twice as hard as solving it for 3 rings. Solving it for 5 rings is going to be twice as hard as solving it for 4 rings, and so on and so forth. Has anyone heard the parable of the king and the chess game? Yeah, so the basic parable is the king offered a reward to someone and said, "What reward do you like?" And the person said, "Well, on the first day, I would like you to put a grain of rice on the first square of the chessboard. On the next day, I would like you to put double the grains of rice on the second square of the chessboard. And on the third day, I would like you to put double the second day's grains of rice on the chessboard." And what's the problem we quickly run into? Yeah, we run out of rice in the world after just a few days of repeating this. So our monks are going to be playing this game to try and do their exponential moves for quite a long time. Let's see how long, assuming there are 64 disks. So if they wanted to solve it for 2, it'd be 3. For 4, 15 steps. For 16, 65,000 steps. For 32, we're already at 2 billion steps. We've still got a long way to go up till we get to 64. So 584 billion years moving 1 disk per second. So you can let your significant others know that they've still got a little time before the end of the world. What about on my computer? My computer's really fast though, so it can move disks much faster than 1 per second like the monks. It does 2 to the 10 operations per second, we said, more or less. 2 to the 10 divided by 2 to the 64, or maybe wrong way around, 2 to the 54 seconds. That's still an awfully long time. It's about 570 million years for my computer to run the calculations solving the Tower of Hanoi for n equals 64. Now, there are definitely some ways that we could think about optimizing this further to bring this number down. But this illustrates why we might actually care about doing this fancy recurrence analysis, because it gives us a sense of how the problem scales. And this is how you figure out that scaling for a recursive function. Paul monks, one thing that's important to know, this is another C tidbit, because unfortunately we do have to interrupt our beautiful discussion of algorithms sometimes, is that C does something called passing by value. Now, passing by value means that inside the computer, it's a little hard to read, there is essentially a photocopier. And when you compile a program, this photocopier is invoked. And what happens is that every time you call a function, this photocopier runs on all the function's arguments and copies them into the new function. What this means is that if you, I didn't bring my live demo today. Anyone have 2 sheets of paper? Someone have 2 sheets of paper for me, quickly? Great, thank you. And a pen. Thanks, Bronson. I wasn't going to catch that, but. Okay. So let's imagine I have my main function here. And my main function has a variable. Let's call this variable x. And what's x going to be? Just someone give me a value. What do we want x to be? 3? Okay, x equals 3. I now run a function called add1 to x. And so like I've just said, when you run a function, C invokes a giant photocopier. And let's say that we want to pass in add1 to x, and we're going to pass in the argument x. So now my photocopier runs, and now on this piece of paper, I have x equals 3. My function runs, let's label them. This is main, put that in M, and this is going to be my function f. So we see our M here and my f here. Now I have my function add 1 to x. So what's x going to be equal to? 4. So let's cross that out. And now I've run my function. I go back to main and I do printf. And I print out the value of x. What value of x am I going to get? 3. Why am I not going to get 4? Because C is copy by value. That means that when you run a function, you're not actually getting access to the original variable in the place that you sent it from. What you're getting is a copy of the variable. So any changes you make inside the function will not be visible inside the place where you originally called it from. Now let's say I move my printf into the function add 1 to x. What will I see there? What number will I see for x? I'll see 4, because there is a copy of x in that function, and that copy has a value of 4. Thank you very much, Corinne and Bronson, for the pen. So this is one very, very common mistake that students will often make when using C, is they'll forget about this. They'll forget that C is passed by value, and that essentially when you pass things into a function, you're generating a copy of them. Now the copies can have the same name, or they can have different names. It doesn't matter whether you call the copy Z or you call the copy X, it's still going to be a copy. So this is just like we did with our demo there, photocopying the notebook and then making changes. So when you modify the input, an argument that was given to a function, after you return, unless you've used a pointer, stay tuned for later in the week, the variables outside are not going to be affected. And this is a really, really key point, which you should come back to a few times and remember. So pointers are the exception, but they're not a real exception. And we haven't even talked about what a pointer is, but just imagine it's a new type. Pointers actually are photocopied as well. But the special thing about pointers is that the value that you're copying tells you to go somewhere else in the computer's memory. And going somewhere else in the computer's memory allows you to access places outside your own function. And that's what we are going to see when we get to pointers in the next couple lectures. So this whole discussion about what variables are visible and what variables are not visible in copying leads us something to what we call scope. Now, you would have seen scope in other programming languages that you've been through before, except the scope rules in C are different and unique. Every language has its own scope rules. So we're going to go through some of them in our time now. So the first is global scope. People here seen Aladdin? Yeah, a few people have. So global scope is a variables that any function anywhere in the program, or at least in that source file, can see. Let's look at an example of global scope. So the way you make a variable, or the way you give a variable global scope, is you declare the variable outside of any function. Typically you do this at the top of the file, just to make it really clear that the variable is global. Now, one thing about global variables is we're actually going to tell you not to use them. Why might you not want to use a variable that's accessible to everything everywhere in the program? And what was your name in the red again? Kelly Roy. Yeah, Kelly Roy makes a really good point. If we have a variable that every function in the program can see and any function in the program can mess with, this makes it kind of hard to keep track of what that variable is doing. And different functions can get in the way of each other, and this breaks a lot of our designed model, our abstraction, where we're trying to separate the program out into neat little blocks, each of which does their own thing. So for the most part in this course, we're actually going to ban you from using global variables. This is not because global variables are bad per se, but we're training you to try and think about your program by breaking it up into chunks. And using global variables is a very quick way of writing some programs. But if you don't break things up into chunks, your programs are going to get harder to debug, harder to maintain, and you're not going to learn good programming practice. So we have our global variable here, and then I have a function void display, so it doesn't return anything. And all I'm going to do inside this function is I'm going to print a variable. And you notice I haven't declared the global variable inside there. It's just going to be able to see that variable that's out in the ether. So my main function runs display. I'm going to change the value of global, and then I'll run display again. I'm not even going to ask you what this one will do because I think it's relatively self-explanatory. So global starts off as 5. Before the change within main, it's 5. After the change within main, it's 5. Seems like a great tool until you actually start changing the value of the variable all over the function, and then you lose track of what it's meant to be. Our next type of scope that we are going to look at is code block scope. And this is scope that is confined to within our curly braces. Remember, that's a block in C that's kind of treated as its own unit. If you declare a variable inside the block, it's not going to be able to be seen by things outside of that block. Similarly, there's function scope as well, where variables that are declared inside the function can't be seen outside the function. So let's look at a couple of demos of how this actually works. It's all great to talk about it in practice, but it can lead to some fairly unintuitive consequences when you actually try to write programs with it. So we've got a few different demos. Okay, I have our variable here. It's in between some curly braces. But if we try and print it, it's not going to work. So let's just try compile it and see what we get. What am I expecting? Yep, does anyone have a guess of what the error will say, more or less?
Not declared in the scope.
Okay, let's take a look. See how clever our compiler is. Okay, use of undeclared identifier x. And then it also complains that I haven't, I'm printing something without having standard io.h. So I've been a bad programmer in multiple ways. You've been a bad Bing. Okay, let's take a look at another one. Here is our next demo. I'm declaring 3 local variables, x, y, and z. Inside some curly braces here, I'm going to change the variables x and y. And notice I'm reusing the name. Okay, so we have our 3 variables, x, y, and z. And here I'm reusing the names inside a bunch of curly braces. So I'm going to make this big. And I will give you a couple seconds to discuss with the person next to you what that second print statement is going to produce. I'm going to remove some of the lines, and maybe I can fit the third print statement in as well. Yeah. Okay, so have a chat to the person next to you. What am I going to see? Can you tell me what am I going to see?
I'm not sure, but the first one I think is 1, 2, 3.
So we're expecting this to be 1, 2, 3. Okay, what about in my next print statement? So let's actually see. And then what I've done here is I've changed z. And now let's put one more print statement to make the demo a little better. Let's put one print statement over here as well. Okay, let's give it a run and see. So as expected, we get x equals 1, y equals 2, z equals 3 up the top. Okay, now when we go in here, now x equals 10, y equals 20, but z is still 3. So one of the things that Leo wasn't sure about is if a variable is declared in like a parent scope, in a scope that you're inside, can you see the variables that are outside of your immediate scope, that are in your parent scope? And the answer in C is yes. So if you have a variable that's declared in the function, and now you're inside, say, a for loop, inside the for loop, you can still refer to the variables that are outside the for loop. You've probably already been doing this already, just without noticing what was actually going on. But what's happening here is I'm overwriting the variables by reusing their names. Now, this is something you shouldn't do. You should always try and keep track of your variable names to make sure that you're not doing what's called shadowing a variable, which means when you use a variable of the same name inside a narrower scope, you lose access to the original variable. Now, that original x that was 1 still exists somewhere in the computer's memory, but there's no longer a name that you can refer to it by inside this scope, because you've just taken its name away and replaced it with something else. Then over here, we change z, so we get x is 10, y equals 20, z equals 100, and I'm not sure why my last one didn't print. So let's close out today. We've only got a few minutes left, but we have time for a very, very short bit of review before we move on to some really challenging stuff tomorrow. So we have our Python versus C review. For those of you especially coming from Comp 101, this will just help give you some pointers to remember the differences. I munched the bread. Okay, some similarities. They're both imperative languages. So remember we discussed different programming paradigms. Imperative just means we go step by step through them. Both C and Python are like that. They both have similar operations available. They both have a print statement. They've both got plus, minus, division, okay? Pretty typical. They have similar control structures. For loops loops exist in both of them. Even though the names might be a little different, the general concepts are the same. We've got if and else. And there's also a wide array of libraries that have been developed for both of them. So there are also some differences that we've noticed. Python structure is set by the white space, so indentation really matters. In C, indentation really does not matter at all, and we saw that in a few demos. In C, our arithmetic is bounded, so we've got our whole challenges with like the 32-bit, with our 2's complements, with our 64 bits. In Python, you don't have to worry about that, because behind the scenes, it's doing this thing where it's making your extra clocks for you as you go. Python uses bool for logic. C typically uses int, although, what do we know about C now? It's going to change, C 2023. I'm not seeing enough smiles. You're not as excited as I am about this momentous year in our history. And this is one of the biggest differences, that Python is dynamically typed, so you don't have to say what type of variable is. And in C, variables are statically typed. Once you say what type of variable is, you're stuck with it. Python is very much batteries included. What this means is there are like list types, there are sets, there are all kinds of things that are very easy for you to use. C doesn't have any batteries at all. It's all up to you. C lets you mess, though, with pointers and memory, which is fun. All of you should be terrified, and that is what we're going to spend the rest of this week on. Thank you very much, and I will see, hopefully, all of you tomorrow.